Hi everyone. So today we're looking at section 3.4. So as you can see, this is going to be about graphs of polynomial functions. Now, so far we have talked about graphs which were straight lines, and they come from polynomial functions that either have degree 0 or degree 1. So those guys are straight lines. When it's a second degree polynomial, which is what we call as quadratic equations, of course we know those functions are going to be parabolas. So in this section, we're actually going to be looking at graphs for polynomial functions where your degree is actually going to be greater than 2. So to talk about drawing good graphs, we of course need to understand the symmetry for the function. We need to talk about what kind of behavior our graph has at its x-intercepts, and then also the leading coefficient will tell you what kind of shape your graph will have. So those are going to be some of the things that we are going to be talking about here when we look at these graphs. So before we can get into the discussion about looking at the graphs for these functions, we do need to understand the intermediate value theorem. So basically it says that a polynomial function takes on every value between any two of its values. So what this really means is that if you are looking at 2 points on the graph of your polynomial function, the idea is for every value going from that first point to the second one, you are going to have a continuous curve, which means there's a value that exists for each point, which is going to be in between of these two values. So if you remember, we had talked about the greatest integer function back in chapter 2 when we had looked at piecewise functions, and your greatest integer function, of course, kept making these jumps. So this is something that does not happen in polynomial functions when we're talking about this intermediate value theorem, because we are saying all those values in the middle are going to exist and you are going to get a nice continuous curve. Okay, so there are going to be no jumps like you have in the greatest integer function. So just your definition for the intermediate value theorem, so you can kind of look through that. So let's talk about the symmetry for these functions. So remember, again, in chapter 2, we had talked about odd and even functions and the kind of symmetry they had. So of course, if you're talking about an even function, then we know they are going to be symmetric about the y-axis. Right? And the idea is if you put negative x in your function and end up getting the same value as the original function, that's how you know you have an even function. For odd functions, they have symmetry about the origin, right? And in this case, if you put a negative x in your function, it actually ends up making your entire function a negative function. So those would be the two types of symmetry we'll talk about. And then for the symmetry for quadratic functions, because quadratic functions, which are going to be functions that look like this, are not going to have an odd or even function because they have both odd and even powers in it. So these guys, remember, bring their own symmetry because they are going to have their axis of symmetry at x equals negative b over 2a. So quadratic functions, which is your second degree polynomial, will bring their own symmetry. So let's look at this example over here to talk about the symmetry of this function. Now remember, one thing you can naturally do is just look at the exponents on your x variables to see if those are odd or even numbers. So if all the exponents on your function are going to be odd numbers, you have an odd function. If all the exponents on your x variable are going to be even numbers, then you have an even function. Okay, so that's one way of doing it. And of course, the other way is plugging in the negative x. So let's take a look at this first example here. So we've got f of x equals negative x to the third power minus 4x. So of course, you should be able to see that this is the third power over here, and then 4x, x itself, has the first power. So both 3 and 1 are going to be odd numbers. So just by looking at those exponents, we can say this is an odd function, and if it is an odd function, it is going to be symmetric about the origin. So the best way to remember is odd function starts with an O, origin starts with an O, so they're both going to be O and O. So that's a good way to remember. Odd functions are going to have symmetry about the origin. Okay, the other way that you can identify if you have an odd function or not is by taking your function and replacing your x with negative x. So you will have negative, and then instead of x, we're going to write negative x to the third power minus 4 times, and again, instead of x, replace that with negative x. Now here, for the first part where you have negative x to the third power is basically multiplying negative x into itself 3 times, right? And if you multiply these, the two negatives will become positive, but then you still have a third negative sign left behind. So this will actually end up making this a negative x to the third. So what happens is, since you're going to have a negative sign left behind from the x to the third, this negative here and then a negative sign from here, these two negatives will end up becoming positive, and you end up getting positive x to the third over here. And then again, multiplying this negative 4 with negative x, multiplying negative and negative again will end up making it positive, and you end up getting positive 4x. Of course, we did not get the same answer as the original problem, because now this is not equal to the original function that we started out with. Because if you equal the original function, then you know it's an even function. So of course, since we did not get the original function, we know this guy is not an even function. Now to check and see if it's an odd function, what you do is you take your original function and you put a negative in front of it and see what you get. So if I put a negative in front of it, you're going to distribute that negative sign inside the parentheses, which will end up giving us negative times negative is positive x to the third. Negative times negative is positive 4x. And this is the same answer we got when we just substituted negative x, right? So that's the same, this guy is the same answer as this one. So in this case, we can say that f of negative x equals negative f of x, and that's what makes this an odd function. Okay? So this is another way of identifying what kind of function you have, and then if it's an odd function, then of course we know it is symmetric about the origin. So like I said, you can just look at the exponents, which will of course go a lot faster, or this would be the other way of finding what kind of symmetry our function has. Now the next thing we want to talk about is the behavior of our x-intercepts. So remember, at x-intercepts, that's where your graph is crossing the x-axis, or it can also be touching the x-axis. So if you look at this graph over here, you will see here at negative 1, 0, our graph is crossing the x-axis, but here at positive 2, 0, our graph is touching, but it does not cross, right? Which means it's not going to go across the line of our x-axis. So this actually depends on if your factor is coming from an even multiplicity or if it's coming from an odd multiplicity. Okay, so let's take a look at our rule over here. So they're saying theorem at the x-intercepts. So we're saying let a be the root of your polynomial function, and k is going to be its multiplicity. So the idea is if you have an odd number for your multiplicity, then your graph is going to be crossing at that ordered pair of a, 0. If k is an even number, then that means your graph will touch, but it does not cross at that x-intercept of a 0. So you can see right here at -1, 0, your -1, 0 is coming from this factor over here, x plus 1, and it's of course raised to the first power. So that's an odd number, right? So that's why it's crossing at -1, 0, but your other x-intercept, which is 2, 0, is coming from this ordered pair, which is x minus 2, and you can see that guy is raised to the second power. So since that's an even number, at 2, 0, our graph is touching but does not cross. So that's basically what you have to remember. The other thing you can help to yourself to remember this rule is just think about the x square function and the x to the third power. So this would be for multiplicity when it's even. You can think of this as multiplicity when it's odd. So when it's even, like the x square function, it touches, right, but does not cross. So that's does not cross, DNC. And when it's an odd, this is even, and then when it's odd, like the x to the third function, this is where it actually crosses the x-axis. So that could be another way you could help yourself remember what this behavior at the x-intercepts is going to be like. Okay. So to put this into use, let's take a look at our second example here. They're asking us to discuss what the graph does at each of those x-intercepts. So is it going to cross at the x-intercept, or basically is it going to touch? So this is our second example over here, x minus 1, and that factor is raised to the third power, and you've got x plus 5 raised to the second power. So you are going to take each one of these factors, set it equal to 0. Okay, so let's move 1 to the other side. So this is going to be the ordered pair 1, 0. And then we are going to move 5 to the other side. So this becomes the ordered pair -5, 0, right? So these are our x-intercepts. Now your x equals 1, or the ordered pair 1, 0, was coming from this first factor, which was x minus 1, and it's been raised to the third power, right? So this had the multiplicity of 3, and then -5, 0 is coming from the ordered pair x plus 5, which was raised to the second power. So that second power is our multiplicity of 2. So remember, when it's an odd number, your graph is going to cross, right? So we will say the graph crosses at 1, 0, and that will actually be, hold on a second, set that one. The graph crosses the x-axis at 1, 0, and then for the second one, since that's an even multiplicity, this is where your graph will touch but does not cross. So we will say for this guy, the graph touches but does not cross the x-axis at -5, 0. Okay, so this is the behavior that we are talking about. And again, remember, this is based on, is your factor raised to an odd or an even number. Okay? Now, the next thing that we want to talk about, and this is going to be for the shape of our graph, is the leading coefficient test. And basically, we want to know is, are the arms of your graph heading up to positive infinity, heading down to negative infinity, as your x values are either going to positive infinity on the right or going to negative infinity on the left. So when we say your x is approaching infinity, we use this symbol to write it. So when you have this x arrow infinity, that means x is approaching infinity or x is approaching negative infinity. So they are saying, since we are looking for an intuitive understanding, we're not talking about precise definitions here. Those are something you actually discuss at a calculus course level. We are going to do a little bit of terminology here, but obviously not getting too much into details with that. So basically, when we're talking about x approaches infinity, that basically means your x value is getting really, really large without bound, right? Because it's going to infinity, which means it's going to keep going. In that same way, when we say x is approaching negative infinity, that means your number is getting really, really small because you're going on the negative side of the infinity, right? So your number is getting really, really small. Again, and it's going to be without bounds because it keeps going. keeps going. So now, as I said, the idea is as x is going towards infinity, where is your y value going? So is your y coordinate going towards positive or negative infinity? And the same thing when x is going towards negative infinity, is your y heading to positive infinity or negative infinity? So again, you can use that same notation of writing y with the arrow towards negative or positive infinity. So to come up with where your y is headed, you actually have to look at the degree of your polynomial. So is it a second degree, third degree, fifth degree polynomial? And then what is the sign on your leading coefficient? So is your leading coefficient going to be a positive number or a negative number? So the degree of the polynomial and the sign of the leading coefficient is what we will be looking at when we are talking about this leading coefficient test. Okay? And so here we're basically interested in the end behavior. Remember I said basically we want to know what the arms of your graph are doing. So again, you can actually kind of think of your y equals x squared and y equals x cubed function. So you know if it's y equals x squared, then the graph of your is going to be a parabola which goes up. If it's y equals negative x squared, then you know the parabola is going down. So the arms are going down. So that can kind of help you visualize what these end behavior of your graph will be like. If you're looking at y equals x to the third, so you can actually imagine this graph on the right here, that little squiggly line kind of graph. Okay, so let me see if I can get that in here. So your y equals x to the third. Okay, I guess I'm gonna do it down here. It's going to look something like this. Okay, for the y equals negative x to the third, so this is for x to the third. For y, for y equals negative x to the third, of course we're talking about reflection, right? So that shape will actually become like this. So even if you can remember these basic graphs, it might help you to visualize what these graphs are going to look like. Again, remember we're interested in the degree of the polynomial. So is it a odd number or an even number when we're talking about the degree? And then when we're talking about the sign of the leading coefficient, we're of course interested in is it a positive number or a negative number? And they're kind of talking about that end behavior again by the degree and sign of the first term. And they're also talking about the smaller degree terms in your polynomials tell you how many hills and valleys you're going to have between the end curves of your graph. So that actually means if you have a degree n polynomial, so if you have a degree n polynomial, that means you are actually going to have at most n minus 1 hills and valleys. So the idea is if it's a fourth degree polynomial, then you will have 3 hills and valleys, right? If it's a sixth degree polynomial, the number 6 If it's a 6-degree polynomial, then you will have 5 hills and valleys. So whatever is the degree of your polynomial, it's going to be 1 less than that. And you can kind of see that here with our y equals x squared function, right? Y equals x squared is a parabola that opens up. But if it's a 2nd-degree polynomial, then you only have 1 hill or valley, right? And in this case, for your y equals x squared function, we of course have a valley here. When it is y equals negative x squared, that's where your parabola opens down. So when your parabola opens down, that means we only have 1 hill. So you can kind of think about it in that way. For your x to the 3rd function, that's a 3-degree polynomial, which means we should have 2, at the most 2 hills and valleys, right? And if you think about this, and I'm actually going to show it to you on this function, even though you can't see, if I just draw this graph a little bit, you can think about this portion being your hill and this one being your valley. So you can think of this part as the hill and you can think of this part as the valley. So that's going to be your 2 hills and valleys. So that's kind of what that little statement is talking about. Okay, so now let's take a look at what exactly does the leading coefficient test tell us. So this is where we're kind of using the limit notation, which is what you normally see in calculus. So remember, we are only interested in the first term of our polynomial. We want to know what is the degree, so that's degree n, and then what is the sign on our leading coefficient. So if your degree is n, which is an odd number polynomial, so your degree 1 polynomial, degree 3, degree 5, degree 7, right? That polynomial would be an odd number. And then if your leading coefficient is positive, so if your degree is odd and your leading coefficient is positive, then we are saying as x goes to infinity, so as x goes to infinity, your function also goes to infinity. And x goes to negative infinity, your function also goes to negative infinity. Now, if you have a odd polynomial, so again, 1st degree, 3rd degree, 5th degree, and so on and so forth, but now your leading coefficient is negative. Leading coefficient is negative, which means, remember, you're going to have a reflection. So now instead of going to positive infinity, when x goes to positive, your function goes to negative infinity. When x goes to negative infinity, your function will go to positive infinity. Okay? So this was for odd functions with positive or negative coefficient. Now if you have an even function like your 2nd degree polynomial, 4th degree polynomial, 6th degree polynomial, and you have a positive leading coefficient, so that means when x goes to positive infinity, your function goes to positive infinity. When x goes to negative infinity, your function still goes up to positive infinity. And then when when your n value is even, so again, still 2nd degree polynomial, 4th degree polynomial, but now your leading coefficient is negative. So again, we're going to see a reflection. So as x goes to infinity, your function goes to negative infinity. As x goes to negative infinity, your function goes to negative infinity. So what you want to do is, let's start with these guys. For even and positive coefficient, you want to think about what does the x squared function do, and this is where both arms of your x squared function go up. For this last one here, where you have even exponent but a negative leading coefficient, you want to think about y equals negative x squared as your function. And remember, this is where both arms of our parabola go down. Let me move this guy closer here. Okay. Now for this first one, you want to think about the y equals x to the 3rd function, because that's going to be odd exponent and a positive coefficient, and this is where your graph has this kind of shape. So as x goes to positive infinity, y goes to positive infinity. As x goes to negative infinity, y goes to negative infinity. And then for this second one, you are looking at y equals minus x to the third, and this shape, of course, is going to look kind of like this. Okay, a reflection from that first function. So you can kind of imagine those graphs if you like. I have actually also included this little table. So what happens when you have odd and positive? So as y goes to positive infinity, x also goes to positive infinity. As y goes to negative infinity, x also goes to negative infinity. When it's odd and negative, you will notice these directions change from that first one. So now y goes to negative infinity as x goes to positive infinity, and y goes to positive infinity as x goes to negative infinity. So again, this guy is y equals x third as your function. Okay, and then this guy will be y equals negative x third as your function. Even and positive, as x goes to positive or negative infinity for both of these, y goes to positive infinity. So this is, of course, your y equals x squared function, where both your arms will go up no matter what. Okay? And then the last one is if it's an even function with a negative sign, as x goes to positive and negative infinity, your y actually goes down to negative infinity, because it would look something like this. Okay? So you've got, in terms of the limit over here, the leading coefficient test, you have this little table to help you out, and then you have this little graph. Excuse me. So this is when you have a positive coefficient and an even function. So you can see these arms basically look like a parabola. When it's an even exponent but your leading coefficient is negative, you can see these two arms here end up looking like when your parabola falls down, right? So that's the kind of shape this graph will have. Now if you have an odd exponent with a positive coefficient, you can see how this arm is going up and this arm here is going down. So this guy here looks like our cubed function, something like this. And then when your power is odd but your coefficient is negative, then this guy kind of looks like this function. Okay, so that's kind of what we need to talk about in terms of end behavior. So let's take a look at this example here. F of x equals negative x to the third minus 4x. Okay, so our first term is this guy right over here. So this will be our exponent n. So n equals 3, right? That's my degree of the polynomial. And then a sub n is the coefficient, and that's actually going to be this negative. And since there's no number, we know the number is 1. So that's the negative 1, and this is the sign of our leading coefficient. So you can see we have a negative leading coefficient and we have an odd degree. So if it's negative and odd, you are actually looking at trying to see how I want to do this. You're actually looking at this little portion of our graph over here. So our degree is odd, our coefficient is negative, so this is the behavior our graphs will have. Or you can think about this little portion here, negative and odd. Okay, so when you are writing this, we will say as x goes to positive infinity, your y value will actually go to negative infinity. And again, I'm actually just using this table to help us out. So the second one, as x goes to positive, y goes to negative infinity, and as x goes to negative infinity, your y goes to positive infinity. So this is one way of writing your answer. The other way, you could write this as a limit, so you can say as x goes to positive infinity, f of x goes to negative infinity. So that's this first one here. We're just writing it as a limit. And we can say limit as x goes to negative infinity, your f of x goes to positive infinity. So that's for this second one. So this is a second way of writing your answer. Okay, and then remember, graphically, so of course this is the direction where your x goes to infinity here, x goes to negative infinity on this side. This one is y goes to positive infinity here, and y goes to negative infinity as you go down. So we are basically saying as x goes to positive infinity, y goes to negative infinity, which means your arm of the graph will be going down in this way. And then for the second part where we say x goes to negative infinity, y goes to positive infinity, your arm will be doing this kind of thing on the left-hand side. So that's the end behavior that we're talking about. So just the three different ways that you can write your answer here. Okay? Now that we have looked at all three of these different characteristics, I guess I could call them, for our graph, now we're ready to put it all together. Okay, so when you're starting to graph a polynomial function, you of course want to look at its symmetry, right? So look for what kind of symmetry does it have. Is it an odd function? Is it an even function? Is it a quadratic function that brings its own symmetry? Find all the real zeros, because once you find all the real zeros, then you can talk about what is the behavior. So that is where you're talking about, is your graph going to cross the x-axis, or is your graph just going to touch but not cross the x-axis? And then of course we want to talk about the behavior of your leading coefficient. So as x goes to positive or negative infinity, where does your y value or your function value go? Now, sometimes all of this information may not be enough, so we may need to calculate several ordered pairs, and it's always a good idea to see if you can find where your y-intercept is. So that will also help us get a pretty decent shape for the graph, for our function. And then of course they're talking about drawing a smooth curve through all the points that you have. Okay, so let's try and put all of this information together here in example 4. So we are given f of x equals x to the 4th power minus 4x squared. So let's take a look at this. So the first thing we're going to do is start with symmetry. So for symmetry, you can see both our x has even exponents. So since both our exponents are even numbers, we can basically say this is an even function. So if it is an even function, it will be symmetric about the y-axis. Okay? So like I said, using the exponents is probably the easiest way that you can check for odd or even functions. Or the other thing would be replace your x with negative x, and you would have negative x to the 4th power minus 4 times, that should be negative x to the 2nd power. Now since this is the 4th power and the 2nd power, that means when we do negative times negative and negative times negative, we will end up getting positive signs, right? Because you have pairs for each of your negative signs. So this will actually end up becoming positive x to the 4th. Minus 4 will actually stay the same, because again, negative x squared will end up becoming positive x squared. So when I put negative x in my function, I still ended up getting the same thing as the original function that I started out with. And when this happens, that also tells us that it's an even function, And even functions, of course, have symmetry about the y-axis. So there's two different ways that you can calculate your symmetry, like we talked about in example 1. Okay, so this was just to show you the second way. So we're done talking about the symmetry. Now let's go ahead and find our x-intercepts. So remember, to find the x-intercepts, we set our function equal to 0. So you will have x to the 4th minus 4x squared equals 0. And I would use factoring to solve this, because you can see x squared is common between both our x terms. So take outside an x squared. I'm taking 2 of the x's out, which means I'm left with 2 more x's from that first term of x to the 4th. For the second term, I took my x squared out, which means I'm only left with minus 4. And then, of course, this is equal to 0. Now that we're done factoring, take each factor, set it equal to 0, and then find your x values. So this guy here, to get rid of the square, we will use square roots, which gives us a positive and a negative root. Square and square root cancel each other out, giving you x equals, square root of 0 is 0, and 0 does not really take a positive or a negative sign, so you just leave this as it is. So your ordered pair for the x-intercept here will be 0, 0. Now let's solve our second factor. So start by moving that 4 to the other side. And then we end up getting x squared equals 4. Same thing, to get rid of the square, take a square root on both sides, which gives us a positive and a negative root. So square and square root cancel each other out. They leave us behind with x, and that's going to be positive or negative. Square root of 4 is 2. So you are actually getting 2 ordered pairs from here, positive 2, 0, and negative 2, 0. Okay? Now the other thing you could have done here, instead of using the square root property, you could have also factored x squared minus 4 into x plus 2, x minus 2, and then you could have taken each one of these, set it equal to 0, and you would have still had x equals negative 2 or x equals positive 2, which would have also given you the same x-intercepts. Okay, now remember, we need to talk about multiplicity. So this ordered pair 0, 0 is coming from the factor of x squared. So since that's x squared, x raised to the second power, that means this guy has a multiplicity of 2. Your x-intercepts 2, 0 and negative 2, 0 are actually coming from the factors of x plus 2 and x minus 2. So each one of them actually has a multiplicity of 1. So for each one of these, you have multiplicity of 1. So remember, when it is an even multiplicity, your graph will touch, but it does not cross. So at 0, 0, that's a multiplicity of 2, which is an even number. The graph touches, but does not cross the x-axis at 0, 0. And then our ordered pairs 2, 0 and negative 2, 0 both have multiplicity of 1, right? And multiplicity of 1 means that's an odd number. So our graph will actually cross at both of these. So it will cross at 2, 0, and it will cross at negative 2, 0. So this would be the behavior at the x-intercepts, and then we have our x-intercepts right here. Okay, so we've talked about x-intercepts. We've got our symmetry. Now the next thing we want to talk about is, of course, our leading coefficient test. Okay, so leading coefficient test, you are of course looking at your, let me write the function here again. We have x to the fourth minus 4x squared. So for the leading coefficient test, we always look at the first term. And so my degree is a fourth degree polynomial, right? And then the sign is going to be a positive 1. So that's the sign of the leading coefficient. So basically we have a positive leading coefficient and we have an even degree. So when it's positive and even, if you don't remember, you can go back to your notes. When it is positive and even, you are actually looking at this section of your graphing, or you can also think about positive and even as being this third row. So as x goes to positive and negative infinity, y goes to positive infinity. So you can say as x goes to positive infinity, y goes to positive infinity. As x goes to negative infinity, y still goes to positive infinity. Or if you want to write this as limit, you can say limit as x goes to positive infinity, our function also goes to positive infinity, and limit as x goes to negative infinity, f of x will still go to positive infinity. So that's two different ways again of writing our results for the leading coefficient test, or just again as a rough graph, both arms of our function will be going up. Okay, so that's kind of what this leading coefficient test tells us. Okay, alrighty. Okay guys, so now that we have talked about the symmetry, the behavior, and the leading coefficient test, the next thing you want to do is see if we need to find a few more additional points to help us get a better idea for the graph. So remember, one of the points we definitely want to find is the y-intercept. So to find the y-intercept, remember this is where we make our x value 0. So our function is of course f of x equals x to the fourth minus 4x squared. So you can think of this as being f of x, or you can replace that with y, and then replace your x with zeros. So of course you're going to end up getting 0 minus 0, which is going to be 0. So that's your ordered pair 0, 0, which was also one of our x-intercepts. So that's the same point, which is also your y-intercept. So before we get into graphing, the other thing I would like to do is draw a table and calculate some additional points. Okay, so how about let's start with -3, -2, -1, 0, 1, 2, and 3. So these will be of course our x values. So put these in your, and again you can use a calculator or do it by hand, but put these in your function, and then let's see what kind of x values, what kind of y values we are looking at. So when you do -3 raised to the fourth power minus 4 times -3 squared, that ends up giving you a y value of 45. Now since this is an even function, for +3 you will also get the same answer. So for +3 also you'll get a 45, and of course you can, like I said, plug it in your calculator and check your answers. At -2 you are going to get a 0, which means at +2 also you are going to get a 0. And remember, -2, 0, and +2, 0 are also our x-intercepts. So, of course, no surprise you got those answers. And then let's check with -1. So with -1, you are going to get -3 as your answer. So that will be the same thing for +1. And at 0, we have the answer 0, because remember, that's this point that we just found, our y-intercept, which also happens to be our x-intercept. So this should also help us a little bit with the graphing of our function. So now let's go ahead and select our x and y coordinate plane, right? So we've got our x and y. So this is 1, 2, 3, 4, 5 maybe. 1, 2, 3, 4, 5. Okay, so +5, -5. Now here's what's going to happen is, unfortunately, of course, we will not be able to get the number 45 on our y-axis here, but at least it gives you an idea of where your point is headed. So let's do 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Okay, and then we'll use these points to help us graph our function. So we've of course got the ordered pair 0, 0 right at the origin. At +1, we have -3. At -1, also we have -3. At 2, 0 is our x-intercept. -2, 0 is our other x-intercept. And then of course at +3, you are at 45. So that's going to be, I don't know, somewhere over there. At -3, it's at 45. So of course it's going to be going up somewhere over there, right? And then if you try to draw a smooth curve from all of these points, you should actually have a graph which will end up looking something like this. This arm will go up, and then this graph here will come down, and then go back up here. So it kind of looks like a W-ish kind of formation, and this is of course our function, x to the 4th minus 4x squared, right? So you can see, and my graph's a little off over here, but you still get the idea. You can see we have symmetry with respect to the y-axis. So the idea is, if I basically fold my graph along the y-axis, the two halves of my graph will coincide. Of course, you can see at the ordered pairs -2, 0 and +2, 0, our graph is crossing the x-axis, right? And then at the point 0, 0, our graph touches but does not cross. And so of course we identified that. When we did our leading coefficient test, of course we saw both arms of our graph going up, and of course you can see both arms of our graph are going up. So you can see how those properties come into play. And then another thing I would ask you guys to do is think about what the domain and range for this function is going to be. So now that you have a graph, you may be able to visualize it. So I will say take a minute or so and think about what the domain and range will be. So you can pause the video, come up with your domain and range, and then you can restart the video to see if you got the right answer or not. Okay? So remember, when we are talking about the domain, we are talking about the x values. So as you can see, I am of course using all the points on my x-axis, because this left arm of my graph will be going towards -infinity. The right arm of my graph will be going towards +infinity, and then I am also covering all the points in between there. So your domain is actually going to be from -infinity to +infinity. Now when we talk about the range, we are talking about the y value. So that's of course, you can see the two arms of our graph are going up, which means you're going towards +infinity, but then on the negative side, how far do you go? And of course, you are only going as far down as -3 over here, right? Which means your graph starts at -3 and you are going up towards positive infinity. Now, the other thing we had talked about was if you have a fourth degree polynomial, then you should have at the most 3 hills and valleys. So of course you will see we have 2 valleys and 1 hill in this graph. So we are also able to verify that property that if it's a fourth degree polynomial, subtract 1 and you get 3 hills and valleys. So that also is something that worked out. So you can kind of see how this graphing works for polynomial equations, especially when you have a degree higher than degree 2. Okay, so this was our example 4. Now, I actually also want to talk about how to solve polynomial inequalities. So this is actually very similar to how we had solved quadratic inequalities in the last chapter. So we're going to look at the graphical method, and then we'll also come back and look at the test point method. So we're starting with the graphical method here. So to graph this function, you're going to have to use the same technique that we just saw in example 4. Talk about the symmetry, behavior at the x-intercepts, the leading coefficient test, and then, plotting some more points, we'll try to come up with the graph of this function. So let's start with that. This is example 5. So if you talk about the symmetry here, again, you can see this is an even function because you have x to the 4th power, that's an even number, x to the 2nd power, that's an even number, and for the constant term, we always think about the constant term as being x to the 0 power, so we're also actually thinking of that as an even number. So we again have an even function, and if it's an even function, then of course, just like our last example, this will be symmetric. This will be symmetric about the y-axis. Okay. Then if we talk about the x-intercepts, you're going to take your function, set it equal to 0, and then try to solve that. So in this case, this guy will actually factor into x squared minus some number and x squared minus some number. So that x to the 4th, we're splitting up into x squared and x squared. 10,000 can actually be broken down into 100 times 100. So when I multiply -100 with -100, I get positive 1,000. When I add -100 and -100, I get -200, and that's going to be your middle term. So this is actually a perfect square trinomial. And then each one of these factors can actually be factored further down, so that can be broken down into x plus 10 and x minus 10, and then same thing here, x plus 10 and x minus 10. So you actually have 2 of these x plus 10, so that's to the 2nd power, and we have 2 of these x minus 10, so that will also be to your 2nd power. So if you actually do this factoring, then you can see that we are going to have 2 x-intercepts, one at -10 and the other one at +10. So take each of your factors, set it equal to 0. So we will end up getting -10 from that first one, which will be the ordered pair -10, 0, and then +10 from this second one. So that's going to be an ordered pair of +10, 0, and both of these will have a multiplicity of 2. So of course, if they have a multiplicity of 2, then our graph will touch but not cross. So the graph touches but does not cross at negative 10, 0, and at positive 10, 0, right? So symmetry about the y-axis, it touches but does not cross at both of these points. Now let's talk about the leading coefficient test. Okay, so remember, for this you are looking at the first term of our function. So that's going to be the x to the fourth, right? So you can see we have our degree n, which is 4. Our coefficient, which is the coefficient on x to the fourth, which is positive 1. So again, you have a positive and even exponent. So positive and even, of course, tells us as x goes to infinity, y goes to infinity. As x goes to negative infinity, your y would still go to positive infinity. Or if you wanted to write this as a limit, as x goes to infinity, your function is going to positive infinity. And as, limit, as x goes to negative infinity, your function is going to, that should be positive infinity. So no matter where your x is going, positive or negative infinity, your y is still going to positive infinity. So just like you saw in the previous example, both your arms are going to go up. Okay? Alright, let's see if we can find a y-intercept for this graph, which means we make our x value 0. So that's x to the fourth minus 200x squared plus 10,000. So that would of course be 0 to the fourth minus 200 times 0 to the second plus 10,000. So of course the first two terms will end up becoming 0, which means our y-intercept is actually going to be at the point 0, 10,000. Yeah, I know. That's pretty far away. So this is actually going to be an unusual graph just because our numbers are so large in here. But, I'll show you how we'll need to make adjustments on this graph over here. So just instead of using 1, 2, 3 for our x values, I'm actually going to go a little bit higher this time and do 0, 10, 20, and then of course negative 10 and negative 20. So let's start with negative 20, which is raised to the fourth power, minus 200, and of course that is also multiplied with negative 20 to the second power, and then we are adding 10,000 to that. So that's going to be a pretty large value. Yeah, this guy comes out to be 90,000 as the y value. And of course, since these are even functions, it will be the same thing for positive 20. Now let's check what happens when we are doing negative 10 for our x value. So negative 10 will actually end up being 0, and same thing for positive 10, because remember that's where our x-intercepts are, at negative 10 and positive 10. So those are our zeros. And then of course when we put 0 in for our x value, we got our y-intercept, which was at the point 10,000, right? So hopefully these points will help us come up with at least a decent shape for a graph. It may not be exact, but it'll be close enough. So, okay, let's do this. Our x and y. So we're going to have to change the scale on our graph a little bit. So I'm actually going to do positive 10 here, and negative 10 here, and then negative 10 here, and positive 10 over here. Okay, so we're going to break this up into tens instead of going 1, 2, 3. And again, if you wanted to show where your positive and negative 20 is, you can put that in here also. All right, so let's use this table to come up with our graph. And I actually wanted to make another note here because these are not going to be the same scale on the x and y values. So your x is actually going to be in 10, so it's 10, 20, 30, something like that, right? But our y, because I want to make sure I can show you what the graph looks like, is actually going to be in thousands, which means this positive and negative 10 that you are seeing on the y-axis is actually going to be positive 10,000 and negative 10,000. Because we need to be able to see the entire shape of our graph. So that means at negative 10 and positive 10, we have our x-intercepts. At 0, 10,000, we have our y-intercept. And then at positive 20 and negative 20, remember we were at like 90,000, so which would be above. So that means our graph would actually be going something like this. And oops, what I wanted to do, this guy would be going up something like this. Okay, so this would be our function, x to the 4th minus 200x squared plus 10,000. And you know the reason we're having to do these different scales where, this guy is in the tens and this guy is in the thousands, because if we don't change our scale, we will not be able to see the entire shape of the graph. And just to show you, let me show you what happens if we had used our Desmos calculator to graph this function, okay? Okay, so here we are in our Desmos calculator, and as you can see, this is our function, so x to the 4th minus 200x squared plus 10,000. Let me close this window, and you can't even see the graph right now, right? Okay, so let's bring this in a little. So this is our negative 10 and positive 10, where our graph touches the x-axis but does not cross. But if I keep zooming out, I am still not seeing, because I still haven't made it to 10,000, right, where my graph is crossing the y-axis at. And so I keep zooming out, and we still haven't made it. But look how our graph ends up looking like. And the more I zoom out, it just starts looking like a vertical line. And by the time I make it to that 10,000, you can't even tell that we have a y-intercept there. Now, if I zoom into that 10,000, then you can kind of see where our graph crosses the y-axis, right? But now you cannot see any of the other shape of the graph. So this is why we need to change the scale when we draw this graph by hand, so that we can see what that entire shape of our graph looks like. Oh, this one. So that's why we need to change the scale on our x and y axis to accommodate our entire graph. Now remember, graphing was not the goal for this function. We are actually trying to find the solution for our inequality, which is basically when is this function going to be greater than 0. So let's come back down, look at the graph, and then solve our inequality. So our inequality is x to the 4th minus 200x squared plus 10,000 greater than 0. So basically we are saying, where is our function going to be greater than 0? And of course, this is going to be greater than 0. Let me see, I'll use. So in this portion, my graph is going to be greater than 0, right? Because all my y values are positive. Same thing in this section of our graph. Our y values are positive. Our y values are positive here. And our y values are positive here. Now, since this is a greater than only inequality, that means we cannot use these points right here, because this is where your y value is going to be equal to 0. So I cannot use these points when I'm writing down my solution set. So when you are writing down the solution set for this example, you are actually going to write it as, and remember we always write our solution sets for inequalities in interval notation. So for this leftmost part, we will write as going from negative infinity to negative 10. Remember, interval notation is always in terms of the x-axis. So you're going from negative infinity to negative 10. Now remember, I cannot include negative 10 because that's where your y value is equal to 0 and they're not asking us for equal to. That means you are then going from negative 10 to positive 10, because that's going to be this entire portion right here, right? So you're going from negative 10 to positive 10. So union. Okay, and again, I cannot use positive 10 also, which means you leave it there and then pick it back up after 10 going to positive infinity. Okay, and that was simply because your inequality was greater than. However, and this is just as an extra example, if they had given us this same function, but they gave us greater than and equal to 0, if that was our inequality, then our solution set in this case would have actually just been from negative to positive infinity. You wouldn't have to break it up. But because we don't have that greater than in the question that's given to us, that's why we have to break it up into these three different parts. So this is the solution set that we are looking for here in example number 5. Okay? Alrighty, I think that brings us to our last example here, and this was actually using the test point method. Okay? So if you remember the test point method from last chapter, that is where we first start by finding our x-intercepts. Okay, so let's do that here. Our x-intercepts will be the first calculation. So I have x to the 4th minus 4x squared. So set that equal to 0. The common thing between our two terms will be x squared, so we can factor that out. If I'm taking x squared from x to the 4th, I am left with x squared again. And then from the second term, you are only left with negative 4 because, again, the x squared was taken outside. And I don't know if you remember this example or not, but we actually did graph this example in example 4. So it's actually the same one we're using, but we're not interested in the graph this time. So what I'm actually going to do is go ahead and factor this x squared minus 4 again, because this is, remember, in the format of a squared minus b squared, difference of squares, which factors into a minus b, a plus b. So you can, of course, think of writing x squared minus 4 as x squared minus 2 squared. So that'll factor into x plus 2, x minus 2. So x plus 2, x minus 2. And then each one of these factors will give us an x-intercept. So take each factor, set it equal to 0. This one here, of course, we end up taking a square root on both sides. So square and square roots cancel out, giving you x equals 0. And 0, of course, does not take a positive or a negative sign here we would subtract 2, and we would end up getting x equals -2. And for the last one, we would add 2, and we get x equals 2. Okay, now once you find your x-intercepts, we're going to need a number line. Okay, and the idea is this one basically represents our x-axis. Okay, so let's go ahead and mark everywhere we see our x-intercepts. Of course, we've got 0, we've got +2, and we've got -2, right? So this is where we have our x-intercepts. Okay, then from each section, you want to choose a test point. So we want a test point from here, from here, from here, and from here. Now you can use any numbers you like, but I think I'm going to do -3 here, -1 here, +1 here, and +3 here. Okay, so again, like I said, you can pick any points you like. I just want to keep them simple. And remember, the idea with the test points is now we want to know, are we going to get a positive sign or a negative sign? So using our test points, let's see what we get. So let's start with our first test point, x equals -3. So in your function, remember our function is x to the 4th minus 4x squared. So in our function, replace the x with these test points and see what you end up getting. So when we do -3 to the 4th power, you're going to get 81 minus 4 times -3 to the 2nd power will of course end up giving you 36. So 81 minus 36 will give you 45, but more importantly, that's a positive 45, right? So that means for this portion where my test point was -3, in this part, our function is going to be positive. So all our y values in that little area is going to be positive. Now, let's try our second test point, which was -1. So replace your x value in the function with -1. So this will of course give you +1 minus 4. So 1 minus 4 will of course give you -3. So that tells us in the interval which goes from -2 to 0, not including those endpoints, all our y values here are going to be negative. Okay. Now our test point for +1. So replace your x with +1 and you actually get the same answer, 1 minus 4, which will be -3. So all y values in that interval are also negative. And your last one was x equals +3, so that's 3 to the 4th power minus 4 times 3 to the 2nd power, which will again end up giving you the same numbers, 81 minus 36, which will also give you a positive 45. So all y values in this interval are going to be positive numbers also. So now your inequality was where are your function values going to be less than 0. So your inequality is asking you where are these y values going to be less than 0, which means they are negative, and that's of course going to be in these two intervals right here, right? So that's going to be from -2 to 0, so that's going to be this interval where my y values are negative, and it's going to be this interval where my y values are going to be less than 0. So when you're writing your solution set, again, remember this is just less than 0, right? They are not saying less than equal to. So when you write this, you are going to say it's going from -2 to 0. Stop, because you cannot include 0, and then you would say it's going from 0 to 2. Okay, so this will be -2 to 0 union 0 to 2. Again, if they had told you it is less than or equal to 0, then your answer would have been different. But when they just say less than 0, this is how you write your solution set. Okay? So you can see the test point method definitely goes a lot faster than our graphing method. But again, I just wanted you to be able to see how to do these examples going both ways. Okay, so that was our example 6. So again, this is it for section 3.4. So let me know if you have any questions, and then we'll talk about this in class. All right, guys, have a wonderful day. Be careful, and see you in class next time. Bye-bye.